Hello econometricians, this is the fourth video for Appendix A, and in this one we'll be talking about distributions. Some important distributions, that is. Starting with the familiar normal distribution. So the normal distribution for a random variable x is characterized by its mean and its variance, and is denoted as mu and sigma squared. The properties of the normal distribution are that it is bell-shaped and symmetric, and most of the possible values that can be taken on of a random variable that is normally distributed lie within one standard deviation on either side of its mean. And almost all observations, or at least 99.7% of observations of a normally distributed random variable lie within 3 standard deviations on either side of the mean. The normal distribution also has 0 skewness and a kurtosis of 3, or 0 excess kurtosis. An important feature of a normal distribution is that a linear combination of 2 or more normally distributed random variables is itself normally distributed. Now we'd like to look at probabilities for values that a normally distributed random variable can take, but this proves to be quite hard when we rely on the equation for a normally distributed random variable. So one thing we can do is standardize the normally distributed random variable by subtracting mean from a given observation and dividing by sigma, the standard deviation. And this enables us to look up the probability that some normally distributed random variable lies within some range for any normally distributed random variable by looking at the same table of probability values in the standard normal distribution, which is usually denoted by Z. So for the standard normal distribution, we have mean of 0, standard deviation of 1. And to use the standardized normal distribution table to look up probability values for a given normally distributed random variable x, x must first be converted to the standardized variable called z. That's given by the relation at the bottom of this slide. Usually we call these transformations z-scores. Once we obtain the z-score, or the 2 z-scores for a given random variable, we can easily look up the probability that the random variable x takes on some value between these 2 numbers. So here's an example of applying this. Here you're given the final marks for the entire population of ECO242 students. And you are told that it follows the normal distribution with a mean of 69 and a variance of 9. So, if x equals 69, we can find z equal to 0, etc., etc. And this slide looks at some examples of how to look up values for probabilities for different ranges of x values. And in the lecture notes, I take you through how to do this for a few of these examples. But do attempt all of them by yourself. If there's any difficulty with any of these, please let me know. Another important distribution is the sampling distribution of x bar. So remember that estimators are random variables, including x bar. The mean of a sample drawn from a normal population follows the normal distribution. So x bar follows the normal distribution with mean of mu and variance of sigma squared over n. So this looks slightly different from the distribution of just a plain random variable, normally distributed random variable. Over here, the variance depends on the sample size. And indeed, the larger is the sample size, the smaller is the variance. Now notice that the definition says that the mean of a sample drawn from a normal distribution follows the normal distribution. However, we have this very important theorem called the central limit theorem, which extends this and says that if random variables xi are independent and identically distributed with mean mu and variance sigma squared, then the statistic un converges to a standard normal distribution as n tends to infinity. So this theorem simply generalizes the earlier statement with regard to x bar. There's no mention of drawn from a normal population in this instance. So all it is saying is, it doesn't matter where we draw the samples from. It doesn't matter what the underlying distribution looks like. When we apply this transformation using x bar estimated from that sample, the statistic converges to a standard normal distribution as n tends to infinity. Graphically, this is what it is saying. Drawing a sample from a normal population results in a sampling distribution of x bar. Again, I remind you, when we're talking about sampling distribution, we mean that in repeated sampling, if we sample from the normal population, estimate the mean, resample from the normal population many times, we'll end up with a sampling distribution that looks like this bell-shaped curve. When we do the same thing with a non-normally distributed population, so clearly the graph on the right, the dashed line, is not a normally distributed population. It is skewed to the right. Nonetheless, if we repeatedly sample from this non-normal population and estimate means for that given sample many times, we'll end up with a distribution that looks exactly like the one on the left, or similar to the one on the left, which is a normal distribution, standard normal distribution. The chi-square distribution is another important one for doing inference, particularly when it comes to the variance. So it is defined on the slide over here. If we have a series of independent standardized normal variables, then the sum of these follows a chi-square distribution with k degrees of freedom, where k is given by n-1. Okay, so this distribution is quite different from the normal distribution, even though it's really just a transformation of the normal distribution. Particularly, it's a squared normal distribution. So because it's squared, it cannot take on values that are less than 0. Further, it is skewed right, because the extreme values of both ends of the normal distribution are squared. But it does converge on the normal distribution for large k. And it has mean equal to k and variance equal to 2k. The last two properties not so relevant for us. So this picture shows you the chi-square distribution for various sample sizes. And you'll notice that as the sample size goes up, the closer and closer the chi-square distribution looks to a normal distribution. And then once again, a very important distribution is student's t distribution. So this distribution has two elements. It has a numerator and a denominator. the numerator being a itself being a chi-square distribution. Excuse me, the numerator being a standard normal variable, and the denominator being a variable that follows the chi-square distribution. Now the second sentence on this slide is important. It says that if you have a series of variables which are independent and identically distributed with mean mu and variance sigma squared, then the random variable x bar minus mu over the standard deviation of the sample follows the t distribution. And this will become very useful for inference about the mean. Some properties of the t distribution: it is symmetric but flatter than the normal distribution. Yet it approaches the normal distribution as the degrees of freedom increases, which is what this picture over here shows us. So notice that for small sample size, n equals 2, which is shown with a dashed line, we have fat tails and flatter distribution, whereas for large sample size, n equals 120, given by the thick black line in this instance, we have very thin tails towards the ends and a relatively taller distribution. Also, notice how quickly the distribution seems to converge to the normal distribution as n increases. In fact, there's a general rule of thumb that for sample sizes exceeding 30, the t distribution well approximates the normal distribution. Now, the t distribution is especially useful for making inferences about the population mean when we do not know the value of either the population mean or the population variance. The final distribution presented in the appendix is the F distribution, which comprises two chi-square variables. And this distribution is useful for comparing variances of two distinct populations. It's also useful for multiple hypothesis testing, and will become useful in multivariate regression, which we'll be dealing with next year. For now, I won't go into further detail with regard to the F distribution. So I think we'll end this video right here.